Alright, so it says light is incident at angle theta 1 on a boundary between two transparent materials. Some of the light travels down through the next 3 layers of transparent materials, while some of it reflects upward and then escapes into the air. And they give us a bunch of indices of refraction, and we're supposed to figure out various angles in the picture. Okay, so the picture looks like I have that this is going to be N1. Okay. They mark this as 90 degrees. They mark this as the air. And then this is marked as N2. And then N3. And then this one is N4. Okay. And they give me that index 1 is 1.3. They give me that index 2 is 1.4. They give me that index 3 is 1.32. And then they give me that index 4 is 1.45. Air is 1. And then in the diagram, we have a ray. And material 1 strikes this at an angle of theta 1. And they tell me that theta 1 is 40.1 degrees. Okay. And so then what will happen is you're going to hit here, and some of the energy will reflect. Then going to hit that boundary with the air. Going to refract like this, and mark this one as theta 5. Okay. And we can see that since air is fast, when the little cart hits here, then this wheel goes real quick and this one's still slow, so it's going to bend it out that way. So that looks good. And then in this case, this is fast, and then this is slow, or this is slower than that one. So you're going to hit the mud and bend in. So instead of continuing on in this direction, we're going to bend inward. So we come down and hit here. Okay. And then we'll hit between 2 and 4, or 2 and 3. And so we're going to go from 1.4, which is larger than 1.32, so then this is slow, and then this is fast. Faster than that one, at least. And so then when we hit here, this wheel is going to turn a whole bunch, and it's going to bend us back outward. I think I drew too much, but that's okay. We'll pretend it looks better than it does. And we're going to hit here. Then we're going to go from 1.32 to 1.45. So this is fast, this is slow. So we're going to hit, the slow medium again. It's going to bend in towards the normal. And then they mark this one as theta 4. So this is the picture, more or less. This one's a little wonky, but that's okay. Light is incident at an angle of 40.1 degrees on the boundary between material 1 and material 2. Some of the light travels down through the next 3 layers, while some of it reflects upward and then escapes into the air. what is theta 5 in the air, and what is theta 4 in the bottom material. Okay? So, what we're going to do is, what you should notice is that at every surface you can get a reflection and a refraction, and you get a reflection and a refraction, and we only drew some of those. I mean, so when we hit here, it'll bounce back in. When I hit here, some of it will reflect off as it goes down in. Here, some of it will reflect off as it goes down in. Then this one will come up and hit here. That one will come down and hit there. I mean, there's all sorts of rays everywhere. We'll only draw the ones we care about. So very, very few of these rays. And so then what I can mark is I can mark that this will be theta 2, like so. Okay? Now, technically, these were parallel to one another, and so what that should mean is that these normal lines should be parallel to one another also. So these normals should be parallel lines. So I have two parallel lines cut by a transversal, which is the ray in medium 2. This right here. And so then this angle here and then this angle here are going to be what? Yeah, those are the same. Those are alternate interior angles. Those are the same. And so then what will happen is that when we run the calculation from index 1 into index 2, we get this as n1 times sine theta 1 is n2 times sine theta 2. But then the angle of refraction is the angle of incidence on the next boundary. And then I can mark this angle here as theta 3. And then again, what I will have is that this normal here should be parallel to this normal here because the surfaces were parallel. And then cut by a transversal, which is the ray in medium 3. So this one here. And so then what you get is that this angle here is going to be equal to this angle here. Okay? And so then when we run this boundary, then what you get is that this is going to be my n2 times the same angle, theta 2 that we got here, will be equal to n3 times the sine of theta 3. And then when I run this boundary, then this is going to be n3 times the sine of theta 3 is going to be equal to n4 times the sine of theta 4. I wrote these on purpose like this, because those are the same. So they're all equal to one another. So you can actually jump from this surface down to that surface and just solve for theta 4, and I don't have to find 2 and 3 along the way. So that's kind of an interesting result, and it has to do with the fact that the surfaces were parallel to one another, parallel slabs or whatever. And so then what we get is that this is n1 times sine of theta 1 is n4 times sine of theta 4. And we solve for the angle theta 4, so we would divide both sides by n4 and take the inverse sine. And what I get is this is n1 over n4 times sine of theta 1. So that's the Snell's law solved for one of the angles. So this will be something you're going to use a whole bunch. So my n1 was 1.30. N4 was 1.45. Sine of my 40.1 degrees. And so what do we get for the angle theta 4? 40.1. 35.37? 27. I only see 3 digits, so we'll go with 35.3. Sounds good. And I don't think I'll need this one for a second calculation or anything like that. So there we go. So again, with parallel slabs, technically the middle ones you don't need. It's an interesting thing. Now what I want to do is I'm going to have this one come in. We had this reflection off of here, and then it's going to refract into the air. And they want us to find that angle theta 5. And so then what we will get is that this angle is the angle of reflection. So this is also 40.1 degrees. And again, since these surfaces are parallel, then the normals will be parallel. So I have 2 parallel lines, these normals, cut by a transversal, which is the ray that was reflected, like this. And so then this angle here is this angle here, which is the angle of incidence between 1 and the air, 1 and 5, I guess. So this is my theta 1 prime. And so then we can run to solve for theta 5 just by doing Snell's law. So then I would do that n1 sine of theta 1 is n5 times sine of theta 5. And then to solve for theta 5, this is the inverse sine of n1 on n5 sine of theta 1. And so theta 5 is our inverse sine of n1 was 1.3. n5, which is the air, was just 1. Sine of, and this was 40.1 degrees. And so what do we get for theta 5? We get what?
5.69.
I got 56.
There you go. Thank you. Okay. All right.